Okay, so today we're going to talk about linear functions. This is in 9b. And in this section, we're going to basically talk a little bit about slope, and you guys remember y equals mx plus b. So most people at this level of math, you've seen that before. It may not be your favorite thing, but we're just going to kind of talk briefly about it in 9b, and that'll be it for this chapter, and then we'll move on to chapter 10. So it says a linear function has a constant rate of change and a straight line graph, okay? So the rate of change is equal to the slope of the graph. So that's what we're really going to focus on in this section is slope, okay? The greater the rate of change, the steeper the slope, okay? And we'll go over that in a second. Calculate the rate of change by finding the slope between any 2 points on the graph. So I just want to kind of briefly go over here on the side. So suppose I gave you the point 3 comma 5 and the point 2 comma negative 7. Okay, so there's a formula for slope, and the formula for slope is m equals y2 minus y1 all over x2 minus x1. Okay, so what we're going to do is we're going to just name this x1, y1, x2, y2, and we can just pick any preference we want. So what we're going to do is we're going to use this formula. Okay, so we're going to say m equals, and then I'm going to do y2, which is negative 7, minus y1, which is 5, divided by 2 minus 3. So this will become negative 12 over negative 1, which is 12. Okay, now once again, this is the change. Oops. I'll write it out this way. M is the change in y divided by the change in x. A lot of times you'll also see it called rise over run, okay? And that just means if you wanted to graph this line, we would come over here, and then we would say, okay, we have the point 3 comma 5, so we'll go over 1, 2, 3, and we'll go up 1, 2, 3, 4, 5, and we put a point. So what the slope says is this is really a slope of 12. That means that it's 12 over 1. Slope always has a rise and a run. It always has a change in y over the change in the x. The only time it doesn't is in 2 special cases where the slope is either 0 or the slope is undefined. That's not going to come up too often for us, but hopefully you guys remember those are vertical lines and horizontal lines. So we're going to, the slope tells us that if you want to get to another point on the line, you just do rise over run. Okay, so what we're going to do is we're going to rise 12. So I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we're going to run 1. And then we're going to connect the dots, and that is how you draw a line. Okay, so here's this line. So this point, and then if we wanted to calculate, we went up 12 over 1. So this is 12, and that's over 1. Okay, and that's what the slope tells us. And that's how we can use the slope to find any point on a line given the one other point. And I could have used this point, or I could have used this point. It didn't matter. You can always just find another point. In general, we like our slope to always be positive rise, and then the run, we don't care. I'm sorry, we like it to be a positive or negative rise, but the run can be negative, or I'm sorry, okay. I kind of outsmarted myself there. Sorry about that, you guys. We want the run, which is the denominator down here, right? The run. We normally want this to be positive, but the rise, we don't care if it's positive or negative. So in general, you always go right. And again, that doesn't mean it has to be done that way, but that's just kind of how we do it because we don't leave negative signs in the denominator. Okay. So I just wanted to give you guys an example of one. Rate of change equals slope. So that's something they also want to make the distinctions. The distinction in this chapter is that rate of change, so like velocity, is the same as slope. Now we're not going to go in depth into velocity or anything like that, but in a physics class, you would find that the slope and the velocity are the slope of the tangent line and the velocity are two similar things or identical things. And they use the formula change in the dependent variable divided by the change in the independent. But remember, we usually use y to represent the dependent, and X to represent the independent. Okay, variables. Which would mean y over x. Okay, so let's move on. So it says find the slope of the straight line, look at any 2 points and divide the change in the dependent variable by the change in the independent variable, which is the change in the y's over the change in x's. Okay, so that's what they're saying right here. If you guys notice, they did the same thing I did, is they built this little triangle right here, and almost like a ladder, like a stairway. I've oftentimes thought of a slope as a stairway, and it's because, you know, when you draw a line, you know, you could go like this to get to the, you know, if you do the same amount each time. That's what makes lines really nice, is because it's the same amount each time, not like exponential. It's the same rate of change each time you go to another point on the line. And they just, you know, calculated it like I did. So I'm not going to go too much into that. I feel you guys can go over that. So it says a small store sells fresh pineapples based on data for pineapple prices between $2 and $5. The store owners created a model in which a linear function is used to describe how demand, number of pineapples sold per day, varies with the price. So they're basically trying to give us a way to do find out what's the best price to sell pineapples for. So it says, for example, the 0.280 pineapples represents at a price of $2 per pineapple, 80 pineapples can be sold on an average day. What is the rate of change for this function? Discuss the validity of the model. So I normally delete these, but because they had a nice little picture here, I didn't want to. So they said the first point is 280, and we see that's right here, right? And then the next point is 550. $5.50 pineapples. So you can see as the price goes up, the number of pineapples that is sold goes down. So this slope, you see how the slope's going like this? We would call this a negative slope. Okay. So this would definitely be a negative slope. Okay. Then if we wanted to calculate the slope, we could say m equals, or the rate of change equals, okay, and we do the, I'm going to call this my x2, y2, and I'm going to call this my x1, y1, okay? So let's see here. It says you do y2 minus y1. So I'm going to do y2 minus y1 all over x2 minus x1. So that means y2 would be 80 minus 50 all over 5, 2 minus 5. So then we get 30 over negative 3, which we would then say is negative 10. Okay. So they got 30, we got 30, but we went a step further. Okay. We went a step further and found out that, did I do it wrong? No, that's good. 80 minus 50, but then, okay, yeah. So we get a negative slope. Okay. So our m equals negative 10. Okay. So that means that for every, remember the change in y's. So as the price goes down $10, okay. So we say this is 10 pineapples for $1, right? So that means that, and it's negative 10 pineapples, right? So as the price goes up $1, we lose 10 pineapples on an average day that we're able to sell. Okay. So that's how you can kind of use the slope to, you know, make quick little judgments or quick little conclusions, I guess, on what you're dealing with in that particular problem. Okay. So, and then here's they're just doing this negative 10. Okay. So here we have the rate of change rule. The rate of change rule allows us to calculate the change in the dependent variable from the change in the independent variable. So the change in the dependent variable, which is normally for us y, equals the rate of change, right? So that would be m, times the change in the independent variable. Well, that would be x, right? So basically what we're doing, or how can I do this? Yeah, let me come over here real quick. I want to, they kind of word it funny. Okay, so using the linear demand function in figure 9.12, predict the change in demand for pineapples if the price increases by $3. Okay, so hold on, let me get caught up in my notes right here. Okay, so here it says using the linear demand function figure in 9.12, so that's this guy right here. Okay. Predict the change in demand for pineapples if the price increased by $3. Okay, so we know that change in demand, so rate of change in demand with respect to the price in pineapples is -10 per dollar. Okay, so we know the change in demand value is going to be the rate of change, which we know is -10, right, times the change in price, which they told us is 3. So then that means we would expect to sell -30 pineapples than what we would have normally. So we're going to lose the ability to sell 3 pineapples or 30 pineapples. Okay, so this problem just uses this formula here, and they just kind of put it in words for you and show you everything. And again, just working back with the original problem. So general equation for a linear function, dependent variable equals initial value plus rate of change of independent variable. Okay, so now this is what I had my slides mixed up. This one is y equals, okay, b plus mx. Okay, so rate of change we know is m, right? So this is m times, and then the independent variable we know is x. Does this look familiar? Yes, this is our old formula, y equals mx plus b. This is slope intercept form. Okay, so this is the easiest and fastest way to identify a slope and to identify a y-intercept. This is your y-intercept, meaning where the line crosses the y-axis, and this is your slope. So if you have something in this form, you can quickly graph it and you can quickly identify the slope. So I could give you a problem like this. I could come over here. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay. And then I could graph, let's say I gave you y equals 2/3 x minus 1. So what I do is I go down 1 and I put my -1 right there. So that's my y-intercept. I know the graph is going to cross the y-axis right there. Right? This is the x-axis, this is the y. Okay, and then I'm going to rise 2 and run 3. So I'm going to go up 1, 2, and then run 1, 2, 3. Connect the dots, and I have my line. Okay, and that's why this is such a nice, I wrote it kind of ugly. Okay, that's why this is such a nice way to write a line, is because it tells us everything. If somebody asks me for the slope m, I say, oh, it's 2/3. If somebody asks me for the y-intercept, I say, oh, it's -1 commas, oops, yeah, I did it backwards, 0 comma -1. Okay, so I can easily identify these things because right here, I now know that that is my y-intercept right there. Okay, so I just wanted to do those. So in algebra, x is commonly used to be for the independent variable and y for the dependent variable. For a straight line, the slope is usually denoted by m, and the initial value or y-intercept is denoted by b. So that's where we get our y equals mx plus b. Okay. So now it says slope intercept. Okay, so for example, the equation 4x minus 4 represents a straight line with a slope of 4 and a y-intercept of -4. As shown to the right, the y-intercept is where. So again, this is just more of a clean drawing than the ones I do sometimes. So they gave us y equals 4x minus 4, right? So all I would do is I would go down 4. So 1, 2, 3, 4. Put a point. That's my y-intercept, right? That goes right there. Okay. And then what I would do is I would then go up 4, because this is really a 4/1. I would rise 1, 2, 3, 4, and run 1. And then I connect the dots, and I have the same line as them. Okay, so again, just pretty nice and clean, easy way to draw a line. Okay, the figure to the right shows the effects of keeping the same y-intercept but changing the slope. So a positive slope, m greater than 0, means the line rises to the right. So this is this guy right here. So this is a positive slope, okay? Anything that rises from the left to right, that was what we consider a positive slope, okay? So again, I kind of don't like their drawing. It's all happening on the same drawing. So let me kind of show you here. So this is something with a positive slope. Okay, so let's just do that. So there's that one. Here's another graph. And then let's do another graph. Oops. Okay, so this is a negative slope. M is negative. Less than 0 means negative, right? And then here is m equals to 0. This is a line with a 0 slope. That would be a horizontal line, okay? So a horizontal line have a slope of 0. And think about it. The reason it has a slope of 0 is if you picked any 2 points, remember, slope is supposed to be able to take you from one point to another. So if I pick this point here and this point here, let's call this point 1 and let's call this point 2. Remember, if you wanted to find slope, don't you have to do rise over run? And you have to do how much did you go up to get to the next point? Well, if I'm already here and I'm going to end up here, I had to go up 0. Right now, let's just estimate. This is like, say this is 1, 2, 3, 4, 5. So you had to walk what, 4? So you had to go 0 over 4, but 0 over 4 is still 0. So that's why a horizontal line has a 0 slope. It has a run, but it doesn't have a rise. And just so you guys know, for a little side piece of information, a vertical lines have an undefined slope. So it's not 0, it's actually called undefined. And it's for a similar, so m equals undefined. Okay. And it's for similar reasons that this one is 0. This would end up being like m equals 4 over 0, which we know is undefined. Okay. You can't have this, right? You can't divide by 0 in the real number plane. All right. So the figure to the right shows the effects of changing the y-intercept for a set of lines, but changing the y-intercept, but keeping the slopes the same, okay? So here's the thing. These are all parallel lines. So parallel lines have different y-intercepts, but identical, but their, let's do it this way, but their slopes are equal. Okay, so any two lines that are parallel will always have the exact same slope. And look at it. If you go from this point to this point, you rise this amount and you run that amount. If you go from this point to this point, you rise this. Doesn't it look like the same stairs, right? To go from, oops. And that's because these are parallel lines. They have the same slope. It's the same stairway you would build on each one of them. But they are all three different lines, okay? Let's see how much we have left. Ooh, kind of a lot. All right, so this video is getting a little longer than I wanted, so I'll try to speed it up a little. So use the function shown to the right to write an equation that describes the rain depths at any time after the storm began. Use the equation to find the rain depth 4 hours after the storm began. So they tell us the slope is 0.5 inches per hour. So we know that this is 1 inch every 2 hours, right? And I'm just writing down this, right? That is M. Right, and you could keep it as a decimal. I just sometimes like, fractions better in general. And they'll eventually want us to work with, use the equation to find the rain depth in 4 hours. Okay, so let's see what we got here. So, oh wait, this is a different problem. Okay, so actually, geez, we don't even need to look at that. It looks like since we start at 0, right, we can use this idea that we go over or we go up 1 inch. So I'm going to go up 1 inch for every 2 hours. So I'm right there now, right? And then I'm going to go up 1 inch. And again, I'm right here. I notice that normally your x-axis is going to be time. So I'm noticing that that's time. So then I'm going to go up 1 more inch. And I'm going to go over, and I get right there, right? So I'm building my staircase. Now this would be at 4 hours right here. So what's my height? My height is 2. So based on the graph, the rain depth 4 hours after the storm would be 2 inches based on this data, based on the graph that they gave us, okay? So example 4, until about 1850, humans used so little crude oil that we can call the amount 0, at least in comparison to the amount used since that time. So basically, they're not saying we didn't use any, but in terms of you know, how much is actually worth counting and keeping track of, they're just going to say, let's just call it 0, okay? So 1850 is our time 0, okay? So by 1960, humans had used a total cumulative of 600 billion cubic meters oil. Create a linear model that describes the world oil use since 1850 and discuss the validity of your model. Okay, so let's see here. They give us 2 data values. Okay, so they give us the year 1850, and that is 0 use. And then they give us the year 1960, and that is 600. So first thing I could do is I could draw a graph if I wanted. Okay. And this is just for fun. You know, I don't think they asked me to do this, but. So let's go, you know, 1800. Geez, I don't want to go all the way up to 1960. Let's go by, let's go, this is 1850 is 0, right? You know what I'll do is I'm going to call, so this is 0. This is 1, 2, 3, 4, 5, 6. Okay, so let's go by, I guess, 5s. So this would be 1850. This would be 19, or let's go by 20s, I guess. 1870, 1890, 1910, 1930. This didn't work quite how I wanted. 1950, and then 1970. You know what, guys? The drawing isn't working quite. I'll do it after I'm done, so I can have a better idea of how I want to number it. So the first thing I'm going to do is I'm just going to label this. I'm going to label this as my X1 and this is my Y1. The drawing wasn't working out, and I just wanted to get to this part. So this is X2, this is Y2. So if we want to find M, we can say that M is worth, right? So M is worth Y2 minus Y1 all over X2 minus X1. So in this case, Y2 is 600 minus 0 all over 1960 minus 1850. So this would be 600 over, what is that, 110? No, I'm sorry, 1100. Let me just double check. 1960 minus 1850. Yeah, I was right the first time. 1960 minus 1850, that's 110. Okay, so 600 divided by 110. So let's cancel some zeros, and we're left with 60 over 11, okay? So if we want to use decimals, this is approximately 5.45 as a decimal, if we round off to 2 decimal places. Okay, so now we want to do y equals mx plus b. Okay, so you have a couple choices on how you want to do it. There's one way that the book uses. I always use point slope form to find the equation. This is my preferred method. Your book just plugs a value in and then finds b. I like to use point slope form, which says y minus y1 equals m times x minus x1. Okay, So what this does is you plug in either point, doesn't matter which one. So I'm going to use the first point because it's easier. And I'm going to do y minus y1, which is 0. What's my m? 5.45 times x minus what's my x1? 1850. Okay. So I have y equals 5.45x minus, and then I just get out my calculator, 5.45 times 1850. And that is 10,082. So 10,000, 82. Okay. And if we want to round off, we could say this is y equals 5.45 x minus 10,083 if we want to round off. Okay. So now we have our equation. So this is our equation. Okay, this is our line. Y equals mx plus b. Okay, now the thing is we can now use this to predict anything that they ask now. So we know that x stands for the year, and we know that y stands for the consumption, right? So x equals the year, and y is equal to the amount, I guess, is it consumed or used? Used, let's say used. Okay, so let's see here. They say we have our new model, and it says, as a model for oil consumption, draw the graph only for the years after 1850. Okay, so what I'm going to do is I'm going to call the years after 1850. So could I start it at 0 if I wanted and call that my first? Yeah, I think that would get confusing though. So I'm just going to do, here's 1870, 1890, 1910, 1930, 1950, 1970. Okay, and then this is 1, 2, 3, 4, 5, 6, 7. How much does it go by? Let's go by 100. Oh, wait a minute. Let's go by 5,000. I think we got to go by 10,000s. You know what I'm going to do? I'm just going to do, no, I can't do it that way because I already set up the problem. I was going to adjust it, but it would just be more confusion. So on and so on and so on. Okay. So now we're going to say we go over 5.45 x for every one. So that would be, geez, I think I did it too detailed. Oh, let me see. Draw a graph only for years after 1850. More significant issues where there's a rise in oil consumption has been linear. See, the problem is, you guys, and this is in billions per year. I didn't read the problem thoroughly enough. Right here, what's just messed me up is billion cubic. So this does not stand for 600. This is 600 billion cubic meters of oil. Okay. So what I could have done, I kind of just don't like the way they have it set up, but what I could have done is, let's just say, if I plug in the year, let's say I plug in the year y of, let's say I plug in the year 1960. Okay, so this should be 5.45 times 1960 minus 10,083, right? So what should we get, right? So I should do 5.45 times 1960 minus 10,083. And I get 599. Now, why is that good? Because they told us that we should have got, if we go back up here, for the year 1960, we should have got 600, okay? And we got 599, so that's a rounding thing. So what I'm gonna do is I'm gonna do these in terms of 100 billion. So this is this. Okay, so in the first year, 1850, well, let me do it in blue. The first year, it was there, right? And then it says we go over 5.45. So we rise 5.45 for every 1 year over. See, that's, geez, you know what I'm going to do? I'm going to have to do it this way. Just because of the way I'm drawing the graph, I didn't make it. So this, I'm just going to connect the dots. Okay. So this is what our line would look like. Okay. And I didn't go this way because there is no time before 1850. They said that's pretty much the beginning of our graph, I guess you could say, when the world wasn't really using enough oil to be calculated. Okay. This example is just kind of explaining to you guys that it's probably more realistically at this point, it's no longer growing linearly, it's growing exponentially. We know that population has risen exponentially since the mid-19th century. So a better model for oil consumption would be exponential instead of linear. And think about that. The more people there are, the more oil is consumed. So basically the oil is growing in relation to the population. So it also has to take on an exponential nature. But yeah, that's it for this, guys. I kind of got long-winded on this graph because it was a little bit annoying how to set it up. But yeah, that should be it for this section. Let me know if you have any questions. Take care.